Today I'm going to talk about practical formal verification of EVM bytecode. So I just want to quickly tell you a little bit about Certora, which is where I work. So we have a pretty strong group of formal verification people and also other people. And we have been working on building tools for verifying high-level functional correctness of smart contracts in languages like Solidity, Viper, and so on. So I don't think I really need this slide for this audience, but we have seen a lot of talks about how smart contracts are programs that run on blockchains, and they're often dealing with a lot of financial transactions, and they involve a lot of money. So it is important to verify the correctness of these smart contracts. And if you go to these websites like Rect and others, you'll see tons of examples of lots and lots of vulnerabilities that have been exploited and causing lots of financial losses. So this is where Certora comes in. So the main tool that we build is called the Certora Prover. And what it does is it takes your Solidity source and a specification in a language that we call the Certora verification language. And it does the very standard SMT-based verification that maybe some of you have worked with. And it tells you either that the program matches a specification or it gives you a counterexample. So to give you an example of the kinds of properties you can verify for your program or for your contracts using the Certora Prover. So here we have a transfer function that takes some amount and transfers it from to to, which are two addresses. So maybe one thing you want to know about this function is that the balances, when summed over all the addresses, should be constant. So you can actually specify this property in the Certora verification language, and the prover is actually going to check it for you. And in this case, for example, it will find a counterexample. So it turns out that if the sender and the receiver of this the transfer function are the same address, then this invariant is not satisfied. So you can try out other examples of various specifications you can write, and you can explore the language at the website. Okay, so today I'm going to talk about how we actually do this. So I know this is a scary looking figure, but don't worry. We'll go through this, and I'm going to focus on a small part of this figure. So I kind of lied a little bit when I said that we verify your Solidity programs or your source programs. We actually work at the bytecode level. So the first thing we do when you write your smart contract and you come to us is we just run off-the-shelf Solidity compilers or Viper compilers, and we get the EVM bytecode. And then once we have the bytecode, we actually disassemble it into a register-based IR that we've built. It's called TAC. It just stands for 3-address code, which is a standard way to represent these kinds of programs. Okay, so now once we have generated the TAC, we do a bunch of analyses at this TAC level. And these are all happening statically without actually running the program. So the reason we do these analyses is the results of the analysis themselves are not super important because, well, they are important, but that's not the final outcome. The analysis actually really help in simplifying the TAC itself so that when eventually we generate the verification conditions using, for SMT solving, the verification conditions themselves become simpler. And we're going to see some examples of how these simplifications happen. Okay. So as I said, in today's talk, I'll focus more on this particular part. So the key idea here is we have programs in our TAC IR, and we do various analyses on them, and we get, the analyses help us simplify the TAC further. So the key idea here is by simplifying the TAC before we generate the verification conditions, we have found that the results of the SMT solvers can be more precise, and we can have faster turnouts. And in today's talk, I'm actually going to focus on 2 analyses that we do. In practice, we actually do many more. But the 2 that I'm going to talk about are going to facilitate memory partitioning and resolving external function calls. And we're going to look at what those 2 mean. So before we actually understand, we need to look a little bit at how memory works in Ethereum. So if you never have seen this before, memory in Ethereum is actually partitioned into different regions. And the nice thing about it is that the regions are very separate. So for example, if you do some kind of analysis at the memory level, that analysis result is not going to be valid if you're working on like the storage level, for example. And so there's a bunch of different regions. There's the stack, of course, but there's also memory, there's storage, there's call data, there's return data, and so on. So today we're going to focus more on memory. And so what is memory? So you can think of it as the heap, but we'll see why it's actually not exactly like heap in just a second. So if you look at how memory is allocated in Ethereum, it's just an array of bytes. And if you have seen languages like Java and C, you know that there are these special operators like malloc or new, which are used in order to allocate new memory. But this is not how Ethereum works, right? In EVM, the entire memory is just a single monolithic array of bytes. And anytime you want to do allocation, you use this notion of a free memory pointer. And the free memory pointer is bumped by EVM whenever you need to do new allocations, right? So there is a special slot in the memory which stores the value of the free pointer, and that tells you where you can do the next allocation. So this is different from how memory allocation happens in other languages like C and Java, like I said. And so to give you an example, there are two main operations. So one is, so let's say you want to load the value of some slot. So in this case, I'm loading something from index 4. You get X. Let's say you want to store the value of Y at index 9. You're going to use the mstore operation. This is actually a little bit of a simplification because in practice it's a little bit more complicated. You can only read in 32-byte chunks, it turns out, but for the purposes of this talk, we don't actually need to understand that. Okay, so what's really happening is that all these different memory operations are really just, they're just integers, right? So you can just use arbitrary indices to access the different slots in memory. So what does that mean when you want to model these operations in SMT? How are you going to do that? So because it's represented as an array of bytes, we use the array theory. And we use these read over write axioms in the array theory to represent the reads and writes to memory. Now, it turns out that when you're working with real large smart contracts, there are actually a lot of accesses to memory. So if you want to do it in a simple way, the number of accesses will grow so the number of axioms will grow in the number of memory accesses. So what we want to do is we want to see if we can simplify the program and reduce maybe some of the axioms that we're generating. So to give you a very small example, let's say that you have some mstore operation that is storing the value of X at index J. And you are also storing the value of Y at index I, and then you're loading the value from some index G. Now, if you want to convert this into the axioms, well, first you need to check if J is equal to G, then you give X. If I is equal to G, then you give Y. Otherwise, whatever used to be there before. Now, what if there was a way for you to know in advance that G and I are never aliased? So if you can infer these kinds of facts, then you can actually simplify the axioms, right? So you have fewer branches in these axioms that you generate. And so this is actually one of the things that we do in the static analysis phase. So we do a static pointer analysis of the memory to figure out these kinds of non-interfering regions of memory. And by doing this, we are able to significantly reduce the complexity and size of the SMT queries. Okay, so that's one part. The second thing I want to talk about is external call resolution. So what do I mean by external calls? So if you've done any Solidity programming or smart contract programming, you probably know that these programs are never self-contained, right? There are many contracts that are calling methods from each other, and you want to know what method from which contract is being called. Now, question is, why do you want to know? So if you are doing verification, maybe you can just say, well, maybe external calls do nothing. Now, this, as maybe you can imagine, is a terrible idea because now any verification result you get is going to be unsound. So you can do the other extreme, which is that you can just say that external calls can do anything. So I'm just going to assume the worst. Now, this is sound, but this will give you spurious counterexamples, and it's going to make the results of your verification imprecise. So effectively, what this means is you're just havocing all external function calls. So you don't want to do that. So what we really want is we want to be a little bit more precise when we're trying to reason about inter-contract communication. So what does it actually mean to resolve inter-contract communication? Let's take a quick example to understand how external calls happen. So let's say we have a contract A and a contract B, and contract A is calling some transfer function from contract B. So B, the small b here is an instantiation of contract B, okay? And this function transfer has two arguments, a receiver and some kind of balance. Now, when this gets compiled to EVM bytecode, there is this instruction called a send instruction. And the send instruction takes three arguments. The first one is a selector, and we're going to look at that in just a second. And the other two are just the arguments from the transfer. Now, the selector is actually kind of interesting. There is this notion of an ABI specification, which specifies, it's a standard that tells you exactly how you can encode inter-contract communications. So in EVM, the ABI specification states that the selector has to be this exact thing, right? It has to be the Ketchuk 256 hash of the signature of the function, and then the first 4 bytes of that. So this is specified somewhere in the ABI specifications for EVM. So what do we want to do when we try to do external function call resolution? So just to give you, the byte level information here. So for example here, the first 4 bytes will be the selector, the next 32 bytes will be the receiver, and the remaining 32 bytes is going to be the balance and so on, okay? Because you read in 32 byte chunks in EVM. So the analysis that we have, what it does is it tracks the value of the selector, and it makes sure that other writes to memory are not interfering with whatever is in selector. And so this is the kind of guarantee that the static analysis gives us, and it lets us resolve external function calls in a sound manner. So just to give you a little bit more of an example here, so let's say that you have, at some index called index, you are writing the value transfer, and then 4 indices from there, you write the value of receiver. Then that takes 32 bytes, and then at index plus 36, you write the value of balance, and then at some completely other index, you write some random arbitrary number 44. And then you send all of this, so starting from index to index plus 68, that's all of the, starting from the transfer and receive and balance, all of that, you send it to when you do the invocation of the transfer function. So what we will do is we will make sure that mem of index is still equal to transfer, and whenever you're writing to other indices, those are not aliased with index, right? Because otherwise, you are going to rewrite whatever you had at index. So this is the kind of guarantee that we get from doing this, the analysis at the TAC level. Okay, so those are the two examples of transformations that the static analysis we have enables. And I want to go back to this figure I showed earlier. And in the beginning, I made this claim that by doing these kinds of simplifications at the TAC level, we are able to simplify the SMT formula, and that does help us with performance and precision and so on. So to evaluate that, we did some experiments. So here we have, over the past couple of years, we have done several verification tasks. So we took about 5,000 such tasks. And so each task is actually a verification task. So, right, so you can imagine maybe checking some kind of pre and post condition, or maybe they're checking some kind of invariant for smart contracts. So we took 5,000 such tasks, and we did 2 experiments. So first, we just completely disabled the analyses. And so what that means is that you just cannot resolve any of the external function calls statically. And so this is imprecise. And we found that about 150 of these tasks actually give you spurious counterexamples, which means these are not actual counterexamples. So if you turn on the pointer analysis, these go away. And the second experiment we did is we disabled these memory splitting rewrites. So the rewrites that simplify the read-over-write axioms, we disabled that. And it turns out that actually slows down SMT solving significantly. So for many of the large verification tasks, we were able to see up to 40 minutes of slowdowns when you don't have these analyses. So the key takeaway from this is so SMT solvers are really, really cool tools. They have, people have done some amazing work in making them scale to real-world verification problems. But it still turns out that sometimes if you do a little bit work beforehand, you can actually help the SMT solvers. So here we had some examples of simplifications you can do in your program that can significantly affect the performance and precision of off-the-shelf SMT solvers. So that was all I had to talk about today. There are a lot of other things that I'm happy to talk about. There are lots of cool things that we are doing here at Certora. And if you're interested in any of these things, you can find me later, and I'll happily talk to you. Thanks.
Okay, I have one question. Is there any optimization that you were really excited about that you thought would work great that just did not help at all?
That's a good question. So we actually have, so like I was saying, in EVM, memory has like these different regions. So we have analyses that are focused on memory and then also for storage and call data and return data and so on. So a lot of the analyses that we do on the storage, they're not actually helpful for improving the performance of SMT. They're helpful for other things, but they're not reducing SMT timeouts and precision and things like that. So, we do experiments where we try to turn off some analysis just to see if it does anything. Even for the analysis that I talked about today, if the programs are really small and the axioms are simple enough, then you don't really need these analyses. And in fact, they will have a little bit of overhead, like not a significant overhead, but there will be some overhead. So they're really useful when you have like big programs with complex SMT formula that it generates.
So it seems like you're doing kind of heroic efforts to reconstruct information that was actually present in the source code. And I'm wondering, have you thought of, is there some way to preserve that information so that you're not kind of starting from ground zero with this extremely low level language, memory model and so forth?
Yeah. So we actually try to, so we have this trust but verify mindset. We do actually use a lot of the information that we get from the compiler, right? So the Solidity compiler, for example, gives you the storage layout. It tells you, it just literally tells you, like, here are the different, slots, and these are the offsets, and this is what the type of the information, like the variable is at this location and so on. So we do try to use that information. One of the things that is kind of nice about working at the bytecode level is it does let you, we've found some bugs in the Solidity compiler. And it turns out that the reason that we found those bugs is because we did all this extra work, like you said, tons of work to figure out, where allocation is happening, whether initialization is happening properly, and so on. And in the process, we sometimes, we've seen situations where the analysis is just not working, and we try to investigate why it's not working, and it turns out that the Solidity compiler is doing something weird. And then we go and talk to the Solidity developers, and they're like, yeah, that's a bug. So it's, there's pros and cons, right? Like, we are definitely doing a lot of work that I guess we could have just bypassed if we were working with some of the information in the Solidity source. But on the other hand, it also helps us discover bugs in the compiler.
Is there additional information that you wish the Solidity compiler were generating for you?
Yes, we talk to them a lot, and we always ask if they can, do this extra little thing for us. Like, would be really nice if there was a way to annotate for example, in Solidity, right? Like here is, allocation happened here or something. Like that would be really cool. Something that people have asked in the past is why not just work with Solidity, right? Like why not annotate the programs and do add some more information that can help. So